So there we are. We're recording now. So today is going to be our 12th session together already. Wow, that's a lot. Covered quite a lot of ground. You might remember from last week, or if you watched the tape from last week, that we were looking at, up to this point, mainly first order systems, one independent stock and one minor feedback loop. And we called those basically molecules, right? And we explored their characteristics and properties. And we said, you know, before we go hooking these things up together, we want to make sure we understand how they behave, because we don't want to be thrown a curveball when you put something together and then something happens here and you get something crazy happening elsewhere, right? And we said, you know, if it's linear and has a stock in it, you can often solve the molecule analytically and learn about it, doubling time, half-life, and what have you. But that the signature way of learning about a piece of structure, either a very simple one or an entire large model, is to put it into equilibrium and then shock it out with a variety of test inputs, steps and pulses and sinusoids and noise and ramps and stuff like that. And you're always asking the question, does it make sense? What's happening here? And if it does, you know, check. And if it does something suspicious or just plain wrong, you want to correct it, right? Then we advanced. We said, all right, what happens if we, and then we said, you know, you make big models by hooking these little models together. Then we said, are there larger structures that are still quite simple, larger than a single stock or first order system? We said, well, second order systems, two independent stocks. And we said, if they're part of a negative major feedback loop, we get oscillations, right? So we looked at a whole bunch of stuff in the oscillation family. And that also led us to explore the issue of how does what we're doing relate to the underlying math, right? To ordinary differential equations, and how does one even translate the traditional math into a system dynamics format where it is alleged that adds value. I've always had somebody tell me here and there, I don't see any value to doing that. I don't know, you know, okay, if you don't see any value to doing it, don't do it. But I tried to show how we could take something like Lotka-Volterra, well-known model, and recast it in various ways. And I think it's much more intuitive, and you can learn about it. And guess what? There's feedback loops there. People often don't realize that. I mentioned that I delight in taking famous economics models, or even models made by economists, and recasting them in a system dynamics format, and then showing my brother and sister economists the feedback loops in their own models or in a famous model, and they're shocked because they're just not taught to think about it that way, or to look for the loops, or to analyze a model in terms of its feedback loops. But up to this point, almost all, not all, but almost all of our models have been linear. Okay, so linear models have a lot of nice properties. You can solve them analytically, right? That's a good thing. There's a lot of interesting analysis you can do with models that are linear, or models that are non-linear, but you can linearize them. So there's a whole industry that says, let's take a nonlinear model and make it linear. And there's various ways of doing that, and then apply all the tools of linear models to learn about the characteristics of a model. But at any rate, so linear models are okay. They're nice. It doesn't mean they generate a straight line as a time shape. They can generate all sorts of time shapes, but it's a pattern in the flow equations, right, that tells you whether or not it's a linear or a nonlinear model. So most of our models have been linear. So what we're going to do tonight is start really looking at nonlinear models and the signature way of doing nonlinear relationships. We haven't really done that. We've kind of peeked here and there a little bit of it, and I haven't delved a lot into it. The few nonlinear models we've looked at thus far are sort of traditional nonlinear models, where you say, well, the predator and the prey have to interact, And we mathematically have them interact by multiplying together the stock of the predators and the stock of the prey. And that's okay. That's perfectly fine to do that. But that is not the signature way of creating nonlinear relationships in system dynamics models. We also do a lot with min and max functions, as I think I've mentioned. And, you know, those are quite useful and they create nonlinearities as well. Those are more sharp edged, think on, off, up, down kind of things, but they're nonlinearities nonetheless. But the signature way is a table function. So we're going to look at table functions tonight and all sorts of ins and outs of table functions and some well-known models and some interesting models with table functions. Before we do that, though, I was debating whether or not to do this. I wanted to tie up this let's translate models, traditional mathematics models, into their equivalent system dynamics formulation, at least in continuous time. We can do it with difference equations as well, but I'll save that for a different course. But if we're working in continuous time, let's look at doing that. So I'm going to, oh, hang on here. I thought I opened it and I opened everything, but I needed to open up. So bear with me 1 second here. I just want to make sure that I have everything open that I need opened here. Okay, so that opened. And just as I was clicking on it, I clicked again, and I'm wondering if I opened it twice. Oh, always a fun time. All right. And if we go over here and we share our screen, and we'll go here. Okay, so before we venture into the nonlinear stuff and the table functions and all that, I just wanted to wrap up this discussion of translating the ordinary differential equations into their equivalent system dynamics representation, because we didn't quite tell the whole story last time. We looked at some famous models and whatever, but unfortunately, that's usually not what you see. If you would open a physics book or electrical engineering book or something, you would tend not to see the models presented the way I presented them. The traditional, like the Richardson's arms race model and the Lotka-Volterra model and so forth. So I'm trying to move my camera. So sorry, so I'm in the picture here. There we go. All right. So what mathematicians do, and to be honest with you, I don't blame them, is they try to take things that are very expanded and compress them into much more manageable formulations. So for example, I could, if I wanted to write, I wanted to add up all the numbers from 1 to 100, I could say summation sign I equals 1 to 100, and then I, and then, I could do that. That's the compound way, or the way the clunky way is 1 plus 2 plus 3 plus 4 plus 5, and I could write that all out, right? And when I got to 100 or 1,000 or 1,000,000, my hand would fall off. Or you can write summation I equals 1 to 100 or 1,000 or 1,000,000, whatever I. And that's the same way of, means the same thing, but in a much more compact fashion, right? So with ordinary differential equations, you almost always do not see them presented like Lotka-Volterra and the Richardson's arms race model and Romeo and Juliet, all those examples I showed you, where you see the individual, we would call them flow equations, or two coupled first order ordinary differential equations. What you see is something like this. Okay, so you see we have A times d squared y over dt squared plus b and so forth. Okay, so as soon as you've got a first term like that, you know that the mathematicians have squished everything together, compacted two equations into one. If there was an a times d cubed y over dt cubed plus, and then the next term would have a square in it, whatever, it would be a third order system, and so forth. Okay, so we have two flow equations rolled up in here, and this is the more traditional way of presenting it. Sometimes you'll see this written instead of d squared y, it will be y dot dot, or a times y dot dot on the top, plus b times y dot, plus c times y. It's another typical notation you might see in a textbook or whatever. So at any rate, this further muddies the water as to what, excuse me, what is going on here. But since we got a squared term in there, we know it's a second order system. And we also know we got to get rid of it, because dy dt, we have b times dy dt. dy dt, that's a flow equation, right? And it's going to flow to a stock y, at least if we just, intuitively right here. But this d squared y dt squared thing is no good. We can't just translate that directly into its system dynamics representation. So what do? And the procedure would be the same if it was d cubed y dt cubed, or d to the fourth y over dt to the fourth, whatever. Usually in the textbooks, you don't have higher than let's say a third order system, because it starts to get really crazy, right? All right, so we have to get rid of or recast that first term with the square in it. Now, this is a model of nothing. I'll show you a model of something in just a minute, but this is a model of nothing. So we're just saying it's a generic model. But if you know what the model is about, you could add some context to it. So that'll be the next example. But you have to define something. So we're going to define, so we know we got to get rid of that first term with a y in it. So we're going to define dy dt, this second term here, we're going to redefine that. We're going to call it x. Okay, and then we're going to say, well, if that's true, then it must hold that if we take the derivative of x, dx dt, as long as you do the same thing to the other side, right, you preserve the equality. Okay, so, and of course, and then the constant is just in here in both cases, right? So look at, this is the thing we're trying to get rid of here. That's the first term here. And by cleverness, by taking that second term and calling it x, right? And then taking the derivative, we can say that this first term can be replaced with dx dt. So we can get rid of this and replace it with dx dt. Okay, and that's what we did here. Okay, now remember, dx dt would be a flow equation, right? So we just want to solve for it, and that's pretty easy to do. We got to get b times x and c times y and plus d on the right side of the equal sign. So you just subtract from both sides. And then I don't want this a here. I want to divide both sides by a. And now we have a traditional flow equation, dx dt. And it's going to flow to a stock named x, right? And remember, dy dt is equal to x. So we define that. So here's your dy dt, and it's just equal to x. And it must flow to a stock named y. And of course, y is over here. Notice that it's linear. Oh, I guess I didn't simulate this. Well, if you simulated it, it would oscillate. Okay. Now, what if you have some context to it? So I just opened a physics book and I took this out of here, a spring mass system. So you have a mass on a spring like this. Okay, and you displace it from equilibrium and it bounces around like a shock absorber on a car or something like that. Okay. So again, we see we got this d squared x dt squared thing, and we know that's no good for translating it directly into system dynamics. You got to get rid of it. Okay, but now we have some information about what this thing is about. It's a mass on a spring. Okay, so m is the mass, k is Hooke's constant. I'm assuming it was named after Mr. Hooke. I guess I'm not familiar with that. Okay, but we gotta get rid of this thing. We gotta replace it. So how do we do that? We define something here that's wrong way, according to that second term, right? So in this context, we know that velocity is the first derivative of displacement, right? X is displacement. So the change in displacement, or position, if you were, the position of the spring is velocity. Remember, acceleration, velocity, position. We did that. Okay. So we have our ordinary differential equation now by definition, I guess you might say, right? Okay. And therefore, if this is true, right, then dv dt, we can build that to replace this guy here. Okay, so we put it in now, and we solve for this flow equation. Remember, dx dt is a flow equation that goes to a stock named x. And it's just equal to velocity, and x is displacement, right? So we solve for this flow equation, and there we have velocity. This would be displacement or position. I just called it x. I should have called it displacement and velocity, or position and velocity, and then acceleration. So remember, we said acceleration, if you accumulated it, it was velocity. If you accumulated velocity, it was position. And now you have the thing going, displacing past equilibrium, right? Okay. So I just wanted to, you don't have to do that in this class, and it's doubtful that you would do that anytime. I mean, if you were an undergraduate or a master's student in engineering here at WPI, you would probably encounter that sort of thing, and you could do this if you found it valuable. You guys won't do that, most likely, but I just wanted to tidy that up and say that even in the event where the mathematicians are using their compacted notation for these systems, you can represent represent it in the system dynamics form. Okay, so let me just tap the brakes there. Is that everybody gets the point there? That's reasonably entertaining, I suppose, but and those are linear systems, so you would be solving them in an engineering class analytically anyway, with sines and cosines and all sorts of stuff. But if you wanted a more intuitive understanding of what was going on there, you could do that. Okay. All right, fair enough. So now let's press on to this nonlinear thing and table functions and what have you. Just got to find the right slideshow here, and I'll share my screen again. So hopefully everybody sees S-shaped growth. Everybody sees that, S-shaped growth? Yeah, okay, good. All right. So if you remember back when we parsed system dynamics modeling, and we looked at what each of those terms meant in a lot of detail, when we got to dynamics, we talked about both reference modes, but also families of time shapes, right? We said, you make a picture of a problem. We model problems from a systems perspective, not systems, right? And you get a problem statement, and then you represent it with usually with a member of a family of time shapes. Now, if you have real data, time series data, you can use that. Sometimes you have to smooth it or detrend it or something like that, because there might be multiple modes of behavior going on there. But if it's a descriptive thing, a written thing, somebody's telling you, you can qualitatively, make a picture of the problem, right? And when we talked about the S-shaped family, we said, well, it's kind of a combination. It's not really its own family. It's kind of a combination of the goal-seeking family and the exponential growth family, or the exponential family. Okay, so when you see S-shaped growth, like with the red curve, right? You know, and by the way, if you remember, if you go back to those slides or the video from that, you'll see I have lots and lots of examples from the real world of these time shapes. Like once you're sensitive to them, you kind of see them everywhere, right? So a lot of things undergo this S-shaped pattern, right? And when you see that, that's your reference mode. Then you're going to look for certain things. You have clues as to what you want to include in your model. How you include them is a function of the domain. What are we modeling here? But the sorts of things you're going to look for are, number one, a positive feedback loop. There might be several, but there has to be one dominant positive feedback process that is controlling the behavior of the system at the beginning, and it's generating exponential growth. But at some point, there's an inflection point, and the positive loop gives way or loses its dominance, and a dominant negative or goal-seeking process takes over. Okay, not necessarily an oscillation, but a dominant negative feedback loop. So you need a positive feedback loop process and a negative feedback loop process, okay? And then you need, since the negative loop is goal-seeking, you need a carrying capacity or a ceiling, something that the negative loop is heading toward, right? That would be the blue line here. And then you need an inflection point where the shift in feedback loop dominance occurs, right? And that is only possible with a non-linear relationship. So you need a non-linear relationship. So you need a positive loop, a negative loop, a goal or a carrying capacity, or a ceiling, something where the system is heading. If we're talking about S-shaped growth, it would be a ceiling. And then a non-linear relationship. And the non-linear relationship would typically be describing what happens as the trajectory of the system approaches its maximum or its ceiling, its limiting factor, its carrying capacity. So you have some guidance as to what to look for. Also notice that shift in feedback loop dominance happens when the net flow is at its maximum. So the green line here is the net flow. We're going to build a little model of this in just a second to tidy this up a little better. Nejla, yes.
I just had a quick question. Are the presence of a goal seeking with the negative, is that due to external limits? Does that indicate external limits, or is that internally?
I think it can be either. So let's take it. This is good enough a reason to pop out of here and go to Stella. And let's see. Unpin Stella Architect. I guess that's the one I want. So let's quickly build a little S-shaped growth model here. Let me pull down a slide. You've seen this model before, but not in this context. So let's get a stock down here. Let's get a flow. Let's call it a net flow because it's technically going to be a net flow. And when we want to do a net flow, even though in this context, we're not going to have any outflows, you could. So we want to go in both ways. Then we want a positive loop. So we're going to have, something like growth coefficient. Okay, so the stock, let's say there's 10. I'm going to be a little sloppy here. I'm not going to dimension my equations or initialize it outside here in the interest of time. Let's make the growth coefficient something like, 0.05, I don't know, something like that. And then it's the stock times the growth coefficient. Okay, and then we're going to run this model. I don't know, maybe 100's too many, maybe 30, I don't know. Just make this up and we'll run this thing. And there you go. You have, that's your exponential growth there. That's molecule number one, doubling time, first order positive feedback loop structure and what have you, right? But then we can say there's some sort of maximum. This could be if this is a glass, it might be if it's an 8-ounce glass, it would be 8 ounces when it's full. If it's a city, it's the land mass of the city. Whatever the case may be. And so we might say that it's, I don't know, 40 units of something. We can say stock ratio is going to be the ratio of the stock.
If the stock is sales, it could be the market size.
Yeah, it could be something. Yeah, sure. It could be something like that. Yeah. So stock divided by max stock. If max stock was something that could change, I would probably do 2 slashes just to make sure I don't get a divide by 0 thing going on. Then I would probably say, whatever I call this, it's just simply growth coefficient. I could say normal growth coefficient. And what did I say here? 0.05. It doesn't matter. 0.05. And then we can say effect. I'll tidy that up. The effect of the stock ratio on the growth coefficient. So we'll say the growth coefficient is no longer 0.05. It's the normal growth coefficient times an effect. And the effect can be coming from elsewhere in the system. I mean, not this stock, or it can be coming from that stock. It doesn't matter. And we can say it's the effect of the stock ratio. So the stock ratio is going to be on the x-axis, and we're going to make a quick table function here. Something like this. We say this is going to go from 1 to 0 and 1 to 0. And we're going to, and I'm going to do this in, I'm going to do this in much more slowly when we do table functions in just a minute here. But right now, I just want to get into the,
what's the stock ratio?
The ratio of the stock to its maximum value. So when that's 1,
oh, okay,
then the stock is full. When it's 0, there's nothing in the stock.
Mm-hmm.
Okay. And let's put the maximum value of the stock on the graph. And let's run it. And we got to run it a little, well, we can make this a little bigger. Different ways to do it. Okay. So as you can see, we have that S-shaped pattern there. So we have a positive loop. We have a negative loop. We have a limiting factor. And we have a nonlinear relationship. So we have the 4 components. And we can add, oh, I'm sorry, what I wanted, max stock, right? Oh, not max stock, I want stock. Stock 1. I should have just said stock. I also want on here the net flow. And I want to put the net flow on the right axis. Okay. So you can see where the net flow peaks. That's where the shift in feedback loop dominance from the positive loop to the negative loop occurs, where it's at a maximum. Now, another thing we might, excuse me, we might note is if we have loops that matter, excuse me, turned on, you can see that the balancing loop at the end is contributing, the negative loop is contributing the most to the behavior of the model. And overall, it's 99.96 at the end. And overall, 55% was due to the negative loop, and 44% was due to the positive loop, right? And if we would go, figure out where to put your pictures here. If we go backwards in time, you'll see that changing, right? You can see those numbers changing, and you see the graph changing now, right? So you can see the shift in loop dominance. You see the numbers in the lower right changing. So the reinforcing loop is 68%, 50%. Right there, it switches right there, right around, where are we at here? Time 10.8. And where's the flow, the net flow maxing out? Right around, yeah, right around 10 point. It's a little with the dotted, the dash, it's a little harder to see. But you could use the loops that matter tool to see where the shift in loop dominance occurred as well. Okay. Now, in this particular case, it's not terribly exciting. I mean, it's pretty straightforward what's happening here, right? But when you have a very complicated model and you're trying to understand why it's doing what it's doing, at least in terms of feedback loops, being able to diagnose where there's these abrupt shifts in feedback loop dominance is very important. And sometimes when you get a shift in feedback loop dominance, you don't get anything terribly abrupt. The blue line looks kind of smooth and, nothing alarming here, really. But shifts in feedback loop dominance can cause abrupt changes. Catastrophe theory, tipping points, where the system is going along and then boom, it's suddenly the floor falls out. So that's a feature of nonlinear systems. So like when you talk about climate change, a very divisive topic in the US, and rightly so. It's global average temperatures rising. What the hell does that mean? The average temperature of the globe from the Arctic and the Antarctic and the equator, and what, is that even meaningful? And going back however many years. So there's a lot of people who are skeptical, and the modelers tend to be like, no. So it's a contentious issue. A lot of the debate surrounds, should we just do what we can, but just adapt as we go along? If the seas start to rise and look like Manhattan Island is going to be underwater, call up the Dutch and say, what do you guys do to keep water out of, Amsterdam? And they know what to do, and just do that. And that's okay if the system gradually changes. There's time to adapt. The problem is with nonlinear systems, if you have shifting feedback loop dominance, it can cause an abrupt, out of nowhere switch. And then positive loops kick in and it just rips the system down very fast, and you don't have time to adapt. So my opinion, that's sort of the system's perspective on why with some of these contentious issues, you have to bear in mind that if you just want to sort of adapt or go with the flow, you can be caught with your pants down, so to speak, because suddenly like boom, and then before you know it, the system has declined. So shifting feedback loop dominance is a big deal in system dynamics. And like I said, I love to show my brother and sister economists famous models with which they're familiar in economics or their own models, but redo it in system dynamics and then show them the feedback relationships. And they're blown away usually because they're not taught to think about dynamic models that way. Even difference equation models have feedback loops in them. And then you're like, okay, then they're like, okay, that's kind of neat. I didn't know that. That's, but so what? Well, then you start talking about shifting feedback loop dominance, what have you, and why that's important and whatever. And then they're like, okay, maybe there is something to learn from the SD people that I wasn't aware of, because they're not taught that way. Okay. So back we go to S-shaped growth. So we need these 4 factors when you see that time shape. Now, if you look at the data I showed you earlier on, lots and lots of little snippets like this, where this time shape happens all the time. This is old, but I left it in here for a reason. Here's wine coolers and mountain bikes. So I left both of these in here purposely, even though they're old, because I wanted one that's consumable and doesn't last very long, a consumer non-durable good that we would say in economics. And then I wanted a consumer durable good. So durable goods last on average 3 years or more, and non-durables are consumed or they don't last that long. They have a shorter lifespan. So something like this, is something would be purchased, consumed, and that's that. Something like this, you might have an expensive mountain bike for maybe a lifetime, but maybe decades. One of my brothers-in-law went to IU down in Bloomington, and he used to ride in the little 500. He was a big biking guy. And I used to tease him when he was dating my sister because he used to shave his legs, because when these guys wipe out, they don't want, they minimize road rash. They shave their legs. But he used to brag, I'm talking 40 years ago or whatever, when we were all young, that his bike cost more than his car because he had all the Shimano, whatever gears and what have you. So, anyway, a good bike can last you very long, right? Is my point. In either case, we see S-shaped growth, right? And here we see it on Digital Computers VAX machines. Of course, Digital Computer no longer exists. It was bought up by Compaq, which was bought up by Hewlett-Packard long ago. But I like this because there's data here. And you can see the peak of the quarterly sales. That would be the flow or the net flow. And it hits. That's where the inflection point is, but you see the ordered pairs, the data. There's some projected stuff here, but you can see it. Okay, so let's look at our first model here. This has a lot of interesting things going on. It's called the Bass diffusion model. Now, the first thing to note is everybody in system dynamics knows the Bass diffusion model. I mean, absolutely everybody. It's like the example that's used in every software package, every software manual, every book. Everybody uses the Bass diffusion model. That's the first thing. So if you're going to play in the system dynamics sandbox, you got to know the Bass diffusion model. It was created by Frank Bass, a marketing professor at IU, Indiana University, in 1969. And he did it, this is important, for consumer durables, durable goods like mountain bikes, not like wine coolers or Five Guys hamburgers or something like that. Okay. The second interesting thing about this rendition of his model is that it's a first order system. And you're like, what? I thought you said if there's 2 stocks, it's a second order system. But for the order of the system is the number of independent stocks. So usually that means count up the number of stocks, and that's the order of your system. But you got to be a little careful. They have to be independent of one another. So the reason these are not independent is that the population or the number of households, the marketing people usually use 100 million, and then they just say 100 and they chop off the zero, so it's easy. 100 million households in the US rather than people. And some of them are adopters and some of them are non-adopters, which means the number of non-adopters is the population minus the number of adopters. So if you're writing the equation for the initial value here, the non-adopters' initial value involves the adopters, right? So they're not independent of one another. So it's a first order system. You could easily replace the non-adopters with a cloud if you wanted to, right? The model would be different, but you could, in terms of the independence, you could do that. Now, the model is very simple, this version of it anyway. So the flow equation right here, that's the differential equation, right, is alpha times beta, and those are just parameters, weights, if you will, times the adopters and the whole shebang times the number of adopters, or number of non-adopters, excuse me. So if you would multiply non-adopters throughout the parentheses, it'd be alpha times non-adopters plus beta times non-adopters times adopters times non-adopters. You're multiplying two stocks together. So that's similar to predator and prey, Lotka Volterra, where you're multiplying the predator stock and the prey stock together. In other words, the predator and prey have to mathematically interact to mimic the predators eating the prey. Well, here we have non-adopters and adopters. And Frank Bass said the way people adopt a product, a consumer durable, a mountain bike or something, is one of two main ways: advertising or word of mouth. So the negative loop is and the alpha parameter is the advertising dynamics, and the word of mouth is the positive loop. The more adopters there are, the more there are to tell and convince a non-adopter, hey, you should have one of these too. They don't even have to tell them. They just have to interact. You might go on a bike ride and you see my bike and you say, oh, that's a great looking bike. I want one of those. Or you might talk to me and I say, yeah, it's a great bike. You should have one. Right? So in this simple rendition, alpha and beta control the strength of the advertising and the word of mouth effects. Okay. And if you run the thing, and it doesn't have to be symmetric like this, but in the nice, clean, symmetric case, you have the adopters, the non-adopters are crossing at the inflection point. They're starting, the non-adopters start up here, the adopters grow to there, and then everybody's an adopter, everybody has one. Now, one of the things that Bass assumed, and it was a good assumption for what he was doing, was that if you were an adopter, it meant you heard about the product either from advertising or word of mouth, and you said, I want one. But then he assumed you bought one. Okay. And that makes a lot of sense for this, particularly if this is what 83 to 95 and a good mountain bike lasts 30 years or something, as I kind of said before, long lasting thing. You say, I want one, you become an adopter, and then you buy one. Okay, cool. Well, what about this? What about you hear about a new flavor of soft drink or alcoholic beverage, whatever, hamburger, doesn't matter, consumable, non-durable, but let's think about a consumable. Maybe it's Five Guys hamburgers. Do they have Five Guys in Indiana, Najla? Do they have Five Guys? Okay. So,
yes, we do.
Yeah. Okay. Okay. So there's McDonald's, which my grandkids, for some reason only known to God, they love that place and they hate all these other places like Five Guys. So we got to go to friggin' McDonald's all the time, where they whine, they complain, oh yeah. So I go there way more than I want to, but let's say it's somebody has I got a better hamburger. Okay. And you either from advertising or from your colleague, you say, well, you should go to lunch at Five Guys. It's really good. And I go, okay. So we follow Frank Bass, and I become an adopter, and I also buy. So I want one, but then I went ahead and bought one. And I said, that was really good. Let's go again tomorrow. So what happens in this model here? I'm an adopter, which means I've heard about it one way or the other, word of mouth or advertising, and I want one. But like Bass, I bought one. I not only want one, I went ahead and bought one. Now for consumer durables, it makes sense. But what if it's a non-durable? What if I consumed it, I want another one? Well, you just go and you make a flow back over here. But wait a minute, non-adopters have never heard about it before. So that's like you'd be going through a Vulcan mind erase process in Star Trek or something, and then you have to become a new adopter, hear about it again for the first time. That doesn't make any sense. So this structure kind of fails when it comes to repeat sales. Like if you're assuming if you're an adopter, you also buy. So we have fixes for this. So as I said, everybody in System Dynamics knows this model. Everybody in System Dynamics uses this model, but it has to be modified to reflect particular circumstances. And I'll be showing you some different circumstances as we go along here. Okay, so let's look at the first modification that is interesting. So I believe last time, I think it was, we looked at Jack Homer's model of worker burnout, and I kind of glossed over the table function stuff because we really didn't study them yet. But we got the idea of this idea of worker burnout, where somebody's working very hard on something and then they burn out and they need to back off and reinvigorate themselves, and they do that. But then what do? They go and do it again. They work really hard because they're now energized, and then they burn out again. So it's a cycle. Why is this happening, and how do you make it stop or at least mitigate it, right? And a big part of it was your wiring. People of a certain personality tend to do this. Well, Jack Homer got the idea to look into that phenomena and model it while working on his doctoral dissertation. This is his doctoral dissertation that he was working on, his model of medical technology diffusion. So Jack wondered how medical technologies diffuse into the marketplace. To this day, Jack is a consultant. He has a System Dynamics consultant company. He's a world-class modeler, but he specializes in healthcare dynamics, healthcare policy and whatever. So from the very beginning, Jack was interested in healthcare stuff. So he has a model of, he built a model of the diffusion of medical technologies into the marketplace. Okay, and that's kind of like this, right? How do you adopt a medical technology versus a mountain bike or a wine cooler or Five Guys or something like that? Well, isn't it just the same? Well, not exactly. There are other things going on in the medical world, particularly at the time Jack was working on this, but really today as well. The consumer, the patient, really didn't make the decision to buy, right? It was the physician. Now, I'm sure most physicians give you a choice, right? But most people will defer to their doctor and say, all right, you're telling me, hey, if I take the red pill, I'll get cured. And if I take the blue pill, it might not work. What do you want to do, Mike? Well, I choose the red pill. You're the doc. You went to med school, right? So really, with medical technologies, you're trying to convince the physician to become an adopter more than the patient. So that's a different thing. And there's other things as well that that were involved. And what Jack did is very interesting. In that era, we didn't have, this is the early 80s. We didn't have big data. We didn't have the internet, all the stuff we have now. So Jack produced a data set that he used for the dissertation by going to the Harvard Medical School's library and combing through all the journals, looking for citations and numerical data, literally going through page by page by page, and he built a data set. So that's really old school. That's how you did it back in the old days. You didn't quite have a quill pen and an inkwell, but that was, a heroic effort to build a data set. Now, if you remember Jay Forrester's telling us that, a good system dynamics model is really a generic structure or real typology. It's a generic example of many specific instances. For example, his urban dynamics model was built of Boston, but he didn't call it Boston dynamics. He called it urban dynamics because he felt his model could represent any city if it was properly parameterized for that city. So Jack is saying, or when he set out to do this work, my model of medical technology diffusion should be able to explain any medical technology that diffuses into the marketplace, not just one particular instance. So he gathered data on two very different medical technologies, cardiac pacemakers and the drug clindamycin, an antibiotic. Very different and very different time shapes. Okay. Now, pacing is really an interesting, when I first saw this presentation, it's a very interesting area because I never really thought about it either way, but really cardiac pacing only came into existence in the 50s after World War II. The original kind of concept, I guess, was from somebody somewhere in like the 18th century who dissected a frog and touched some electricity to the frog's spine and its legs jumped. And somebody got the idea that you could use electricity on patients somehow. But they really didn't start doing this pacing stuff until after World War II in the 50s. And it was quite primitive. I mean, you'd have this giant sort of battery thing with cables out of it, and they jam this thing into you. And then you walk around with this stupid thing like an Apollo astronaut carrying your life pack for the rest of your life. But, if your alternative is like, well, but you'll be dead without this, what do you want me to do? You said, well, go ahead and do it, even though it sucks, right? And then over time, the pacemakers have gotten smaller and smaller. And then, Bluetooth technology so it can communicate with a computer right to the cardiologist. And, who knows what Elon Musk is planning for us. You'll be able to think and it'll go right to your pacemaker or something. So over time, the pacemakers got better and better and better. They could do more things and got smaller and smaller and what have you. So it's a very interesting area. So what's Jack's model all about? Well, it's a very big model. So I said, let's look at it in terms of some causal loop diagrams. So right away, what do we see here? Adopters and non-adopters and adoption rate. He started with the Bass diffusion model. Okay, but it's not just the Bass. If there's much more than just that going on here, but so there's a word of mouth and an advertising effect, and the more adopters you have, the more purchasers, and now the adopters are physicians, right? And they're going to cause more of the pacemaking devices to be purchased, which leads to more revenues for marketing expenditures, and then that increases the adoption rate through advertising. Right now, they've dialed back in recent years. In the old days, my understanding was, the sales reps for the drug companies would come in and they would be bearing all sorts of gifts for the physicians, everything from swag, pens and notepads with the company logo to, well, why don't you take these free airline tickets so you and your spouse can come down to our conference in Bermuda to hear about our new drug, and then you're free to do whatever you want for the next 5 days after that. They used to bribe the doc. I guess you can't really do that anymore, but at any rate,
they still do it in veterinary medicine, just FYI. It is illegal in human medicine, but they still do that to us in vet medicine.
Okay, so yeah, it's standard practice still in some areas. But at any rate, the more adopters, the more purchases, the more promotional expenditures, there are more adopters. So you got a positive loop going there. Already from the original Bass model that I showed you, we have a modification. But I just was an expert witness in a bunch of court cases, 4 of them involving the opioid epidemic. And part of the discussion was, did the big pharmaceutical companies hoodwink the doctors into over prescribing opioids due to predatory marketing. And a lot of the conversation was, well, we're sure doctors don't just, look at a brochure, even if it's all false advertising, and go, oh, okay. They do doctor stuff too, right? They talk to their colleagues, they observe other patients, and they evaluate other therapies, right? So in addition to hearing about the new medical technology from promotional materials, they're looking at the performance or the relative performance of that therapy versus some other way of treating the patient. Okay. At least if they're a good doctor, they're doing that, right? They're presumably trying to help the patient, right?
Well, they're also getting feedback from their patient about how efficacious it is. And if it's addictive and their patients are going, this stuff is great, you can see how that can be problematic in this model.
Yeah. So, So anyway, so along those lines, the more purchases you have, the more R&D you can do to improve the product, and the more experience you have with patients who have been given the pill or the device or whatever, as Suzanne is kind of alluding to. In this case, this is Jack's model, not mine, but his, that leads to product improvement. They have more capabilities. You can Bluetooth now, you can, whatever, better performance and better perceived relative performance, more adoption. So we have more positive loops going on there. But this is where, again, it gets a little different from the standard sort of Bass story where you just convince somebody that they want your hamburger, your wine cooler, your mountain bike, but now you're convincing the doctor instead of the end user. And there's also this thing called extent of use in Jack's model. So what he found was that the more something seemed to work, the more the extent of use grew. And so extent of use is the patient profile to which it was deemed legitimate to offer this therapy. So the way I like to describe it is, it's designed for somebody who's dead without it. Do you want it? Sure, of course. Well, that's working now. You're not dead without it, but you can get up from the couch and move about your house at will if you have this. Do you want it? Yeah. So now bigger patient profile it's good for. Well, now, not just the people who are dead without it or can walk around, now you want to go for long walks to keep your weight down. You want it? Oh, yeah. So the extent of use grows again. Oh, now you want to start jogging. You want it? Okay, extent of use grows. And so more purchases, but the relative performance, the bang for the buck, at least its perception starts to decline. Like you're dead without it. Now you're alive. Is there a perceived goodness to this? Yes, it's quite dramatic, dead versus alive, but you can walk a mile or you can jog a mile. The perceived relative benefit because of the extended extent of use isn't as obvious or as dramatic. When we put the slashes in here, and Stella does this for us, sometimes we said there's a box. Sometimes there's a box that says delay. It just depends on the author. There's a delay between cause and effect, the change in performance and the change in the perceived relative performance, but you got a negative loop there. And of course, in any technology diffusion model, doesn't have to be medical technologies, like let's say the internal combustion engine, at the beginning, you get a lot of improvement as you go from the first try to the second try and whatever. But after a while, how many more improvements can we make to the internal combustion engine, right? That you probably can still make some, but you've passed the inflection point and you're just making ever so slight incremental improvements in the product's capability. Yes, Suzanne, sure.
So I think this is a really fascinating model and problem and way of thinking on a couple of fronts, because you're talking about potentially the perceived relative performance of two different entities. One is the doctor and another one is the patient. because you have your purchases are actually done by the patient, right? But the perceived relative performance is by whom?
By the,
The
well,
patient or the doctor?
well, the doctor who's really going to be convincing you to use it. I mean, some people, I'm sure there's cases where a doctor says, I really think you should have A, and you say, no way, I want B. But most people, I think, or at least when Jack was doing this, just followed the doctor's advice. Just say, hey, you're the guy who went to, or gal who went to med school. I didn't, so okay.
I mean, I guess that's an implicit assumption in this model.
Yeah, and today we have all these commercials for all these drugs, right? And I assume the pharmaceutical firms want you to go to your doctor and say, I want this. I saw a commercial, I want this. I guess. I mean, otherwise I don't understand why they would be showing these things, but they seem to think that's a good idea.
A long time ago, that was considered extremely unethical.
Yeah, or illegal.
To advertise or
I think it's illegal in a lot of countries. I don't think a lot of countries allow it. Yeah.
But I think that's the challenge with any model like this, is sorting out whose perceptions are you evaluating related to the actions taken. This, to me, this perceived relative performance and the actual performance can be very different between the client and between the patient and the doctor, but the patient is actually doing the purchase. I mean, there's lots of times you can prescribe something and people will not act on it. They will not purchase it. I just think it's an interesting problem. Like, how do you communicate those implicit assumptions effectively in circumstances like this? Because it goes back to say again, how there is a value in the causal loop diagrams, but there's a lot of stuff embedded in here that can be misdirected, until you start building a simulation.
Okay. Fair enough. Now, the delay, the double slash thing there was this. And again, this is old school. But back then, the way the doctors found out about how the drug or the therapy was doing was they would read medical journals. And what you'd have to do is do studies. So you'd have patients under observation. This is in his model, is my hand drawing of it. And new patients would come in, and patients would leave the study, they'd pass away, or they were followed long enough. And then you'd analyze the data, you'd write a journal article, the Journal of the American Medical Association and the New England Journal of Medicine, Lancet, and all these. You had a backlog of articles, so it'd take a while to get out. And then the article would be published, and then you'd read it and you'd say, aha, and then that would generate follow-up studies and what have you. So that was the cause of the double slash there in his model. And then, of course, that would generate competition and change the perceived relative performance. Now, Jack, as I mentioned, went and handcrafted these data sets. So here we have initial and replacement annual pacemaker implantation. So those are flows. And here's actual and simulated. And he didn't have an algorithm to fit. He manually fit the model to the data. He has another paper that I remember him presenting this in 1983. I was a student, and I remember going to his session, and he presented this. And what he was showing was partial model testing. It didn't have anything to do per se with medical technologies, but he showed how he first tried to represent this with a first order delay, and it didn't fit very well. And when he tried a third order delay, it fit pretty good. This is without an algorithm grinding and finding. So it's qualitatively a pretty decent fit, given that he didn't back then have the technology to fit it with an algorithm. And here we have pacemaker purchases, new ones in total. And you can see there was a peak here and a fall before it took off again. Fraction of physicians. So you can see nobody was doing pacing in 1960. And then you had the exponential growth And then pretty much everybody, cardiologists, it's a routine thing now. And here's the fraction of patients. So I think there might have been some kind of probably medical scandal or patients having problems or something. I don't know. I probably read it years ago. I don't remember, but still it fit the data pretty well. So then this is what was really interesting. Jack said, now I want to switch gears to something very different, clindamycin, an antibiotic. And he found he had only make 5 changes in his model, either to a table function or a parameter. So unanticipated side effects, not significant with pacing, severe but rare with the antibiotic. It was both the ointment and the oral medicine. So some people get the runs from taking it. Antibiotics can upset your stomach. Improvement potential. You're dead without it. With it, you live. High. Clindamycin. Here's another ointment for your cut. Low to moderate. Initial resistance. I'm going to cut you open and stick this thing in you, and you're going to have it for the rest of your life. What? I'm going to put a different kind of salve on your cut or give you a different pill for your ear infection. Okay, not a big deal. How easy is it to observe relative benefits? Easy with pacing. The guy can't get out of his chair. Now he can. Versus, okay, I put this on your cut and your cut healed. Yeah, but if you put Neosporin on it, it would have healed. Okay. Duration of treatment, rest of your life, long for pacing, short and acute for the antibiotic. So by just changing those 5 things, he was able to nail down actual and simulated. Now, notice the difference in time shapes here. Clindamycin. So that looks more like not S-shaped, but goal-seeking, right? Just pure goal-seeking. Fraction of patients, much smaller, as you can see. Okay, so then we've already covered pandemics, but so the BAST diffusion model is also very similar to how you would model the spread of a rumor or the spread of a disease. And we already covered the pandemic thing earlier in the term, so I'm not going to take class time to revisit that. But rather than a non-adopter talking to an adopter and deciding that they want one too, or through advertising, now you're spreading the disease. You're interacting and spreading the disease, or spreading the rumor. Adopter, non-adopter. I didn't hear the rumor. I've heard the rumor. And the people who heard the rumor have to give it to the person who didn't hear the rumor. So it'd be the same structure in all those instances. Now, let me show you another model that I've built that uses a souped up version of the BAST diffusion model. So you can begin to see it's only a starting point. It primes the pump, but you can take this thing in a lot of different ways. And actually, I've been using this in the second course that I teach in system dynamics, this model that I'm going to give you a peek at now. Although I've been thinking about changing it, but I might not change it. I'm not sure what I'm going to do here. But let me share my screen again, because this is kind of a neat model. Now, it's still in VenSim, and I call it Filter 10. And this was what, April 26, 2019. So this is one of, just as an aside, this is one of my stylistic things that I do, that I like to put in information when you open a version of one of my models. You know, who did it? Well, it's me. What's my email address or the author's email address? When did this thing happen? And a brief blurb about what's going on here. So I added an accounting sector, or counting sectors, to filter 9, which was the previous version of this model. There's nothing magical about doing this. This is simply how I like to keep track of a bigger model as it's being built. So I know, so others could see what I've done. Like if I would give this to you, or all of the filter 1, filter 2, filter 3, and you would, in a class, and you'd be like, okay, what did he do here? Versus I might not remember what the heck. I don't remember what I did in filter 10. I just remember now that I read it. So I did that a couple of 3 years ago, right? So it's useful to, you got to develop a style so you can keep track of your stuff, is what I'm suggesting. And this is when I used to use Vensim, this is what I would do. And I would always call that introduction. Okay, so you can see over here, there's a lot of sectors and subsectors, right? So what's happening here? Well, we had a master's student from China visiting with us, and she became interested in system dynamics, and more specifically in a problem that she was experiencing back in China, and that was bottled water versus filtered water. So there was a battle in the major cities in China over should households adopt a bottled water system for their drinking water, their cooking water, dishwashing and whatever, and not for like washing a car or something, but for anything that's going to be consumed, even laundry, perhaps, but certainly for consumption stuff. Do you want to use bottled water, either these giant jugs or the little bottles, or do you want to use filtered water? Now, a water filtering system required you to buy a contraption, and water would come in from the municipal system, go through this process, and come out clean on the other end. But there was an upfront cost to the machine. It needed parts, new filters or whatever. It would break down. You need maintenance for it and whatever. But the point is, just drinking tap water was not a good idea because of the polluted water system. So you had to do something. On the other hand, with the bottled water, you might live on the 30th floor of an apartment building. You're lugging these giant things of water up 30 flights of stairs and what. So there's pros and cons to either one. So she was interested in the battle between filtered water and bottled water. That's the story. So she did a master's thesis with this, and she needed some help. She got stuck and she seemed lost. And I was not her supervisor, but I said, look, why don't you drop by? Let me take a look. And so she showed me, and I started making some suggestions. She started incorporating the suggestions, and she ended up doing a solid job, a nice job. Then she left. She graduated and left, but she left her thesis. And I thought, she moved the ball up the field. Okay. And it was master's student, and she wasn't just taking system dynamics courses. She was taking all different. So she had, I don't know if it was 1 or 2 courses. So, she didn't have a ton of training. So I said, let's give her full credit for starting the ball rolling down the hill, but maybe we can extend what she did. And that's what I did for this class. So this is my extension of her thesis work. All right. So what about this Bass diffusion model thing? So looky here, we got adopters now, and there's really implicitly non-adopters. I have a cloud there, but we notice that we have market non-adopters. Those are households that are trying to decide what they're going to do. All right, so these would be like young people setting out on their own. They're leaving their parents' home, and they're going to, or moving to a new city. And they got to decide, am I going to buy one of these contraptions, or am I going to be lugging bottles of water and jugs of water around? What am I going to do here? Okay. And they have 2 choices, bottled or filter. And they're going to pick one of the 2. So over here, they're going to be an adopter of bottled water or filtered water. But then as their experience with the technologies unfolds, they can switch if they want. Okay. There's nothing in here that says you can have both at this point, but I suppose that's possible. So there's a whole lot going on here. So we don't want to really get into, there's attractiveness stuff here. There's a whole lot of stuff happening there. There's what else we got here? Pricing sectors. How do they price their product? We got, I just started doing the accounting sector here. So in this version, so it's very simple at this point, but the accounting sector would be much more sophisticated, inventories and whatever. So there's a lot going on here. I don't know if I have it here. Hang on. I don't know if in this version I have it. Let me look here. to data. Okay. So you can see there's the data that Shia, the student, collected, and I fit the model to the data. It fits really good, right? That's for bottled water, and then for market share for filtered water. Okay, so we got it kind of tuned up to her data set. And you can run it forward, you can see that 2021 was when we completed. So I don't want to go into this model right now beyond it. I just wanted to show you guys, again, that you start with the concepts in the BAS model, but it can be much more sophisticated than this. We did one, I did it with a guy from Yale who visited with us for a year. He's a visiting prof. He was on sabbatical, and he was interested in zero emission vehicles and the struggle between ZEVs, essentially electric cars, and internal combustion engine vehicles. So you'd have people who were in the market for a new car, and they'd pick one or the other based on a whole laundry list of relative price, relative delivery delay, relative features, availability of infrastructure to charge your vehicle or not. And then the car would wear out and they go back into the market, and they didn't switch like here, but they would, when the car was old, they would go back into the market, and then they could buy another of the same kind, or they could buy a different kind. So this sort of mechanism, this modified BAS thing, is used a ton in system dynamics modeling, but everybody starts with the original BAS model. Okay. All right. Whoop-de-doo, as Archie Bunker would say, whoop-de-doo, whoop-de-doo, right? Let me get rid of this.
They may not know who Archie Bunker is, Mike.
But if they knew who he was, it's from a TV show from the early 70s called All in the Family.
But you should tell the professor that he just needs to make the electric vehicles cheaper. That's what I learned from my recent car buying experience. They're still
Yeah, the government subsidizing it, and that's right. Yeah, there's all sorts of, and we did that. I don't know, like 20 years ago or something like that when we did that original work. But it's kind of an interesting. I think I showed you guys a sector diagram from that model. If I remember correctly, we're talking about sort of overviews of. Yeah. Okay. All right. So let's talk about table functions now. So we know this. All right. So the next topic here is formulating table functions. And this is the signature way of making a nonlinear relationship in a system dynamics model. So let me have my, they call these jam boards or whatever the heck they are.
Are there several ways of doing it? I mean, I've been meaning to ask you this for a long time, but this is the fundamental way of creating nonlinear relationships.
Well, yeah, anything that deviates from the linear template makes the model nonlinear, right? So min functions, max functions, multiplying stocks together, dividing one stock by another, raising a stock to a power that isn't one. I suppose if you I guess if you throw an if then else Boolean logic, it makes it nonlinear. I guess not entirely sure what a mathematician would say about that one. But the table function is really the signature way, the Forrester way of doing it. And we've already seen this. You have typically, a normal value of a parameter, let's say. Like if you look at the Forrester's world model that we have the simulator up there, he does this all over the place there. And then you have the coefficient or the parameter. We did this a moment ago with that model. So this is the normal coefficient. Call it coefficient 1. And then you have, an effect over here. Effect number 1, let's call it. and it modifies the normal value. And this would be some kind of table function, typically. Now, you can have any number of these. So you could have, another table function, effect 2, and so forth. So in the world model, like the death rate there's all sorts of influences on the death rate and the birth rate in Forrester's world model. If you go back and look at those simulators, that simulator. Okay, and then this coefficient goes and does something else. So this is very common. So it would be, in this case, it would be the 3 are multiplied together. These 3 things are multiplied together. When these things are at their, I should use a different color. When these things are at their normal level or normal value, when things are normal, they typically have a value of 1. So when whatever's going on these axes here, when they're normal, when they're at a place where it's basically saying there's no pressure to change that parameter, then it would be 1 times 1 times the normal coefficient here. So it would leave it alone, right? And then as whatever's on the horizontal axis here changes, the effect would be above or below 1, typically. Tuning this parameter here up or down, depending on what's happening. Okay. So that's the signature way of using a table function. Is this the only way to use it? Absolutely not. You could have on this horizontal axis, you could have time. Right, you could have time on this axis, and you can have data in here. That's okay. And then you say, fit the model to these data. That's a way to do it. So this is not the only way to use a table function, is what I'm trying to say. Yeah, Suzanne, sure, what's up?
So when you talk about it going through that place where there's no pressure on the system to change, essentially it's at that moment in time, it's hit equilibrium, right? Is that right? For that little fraction of time.
Well, it could be equilibrium, or there's just no pressure for change and from that effect in the system. There might be pressure from other things going on. But these things are all drawn ceteris paribus. Everything else remaining the same. You're only looking at that relationship. But equilibrium would certainly be a time when that would happen. Absolutely. Okay. So how do we draw one of these contraptions, or how do we make one of these things? Well, we're going to do it in Stella as we go along here, but for now, there's a bunch of things we want to know about. So the vertical axis is going to be the effect. And of course, these are generic concepts. So the effect of what? We don't know. Okay. Typically, there's a value of 1 here somewhere. It might be 0 to 1, so it might be the maximum value. It might be 1 to 10. It doesn't have to be in the middle. I'm just putting it there for now. Then over here, we almost always have a ratio. Okay, we almost always have A divided by B, something divided by something. Okay. So we might, for example, have the ratio might be demand for something divided by the supply of something. Or it could be something divided by the initial value of something at the start of the simulation. It could be something divided by the desired value of something. Okay. So in this case, when the numerator and the denominator are the same, the ratio will be 1. And presumably when it's 1, you don't want the effect doing anything. You want it to be neutral. So 1, 1 is almost always in a table function. So when supply and demand are balanced, there should be no effect on price. Let's say, leave price alone. We're good. Whatever we're making is being sold, right? When my inventory is at its desired level, don't start having a sale. I like where it's at. You know, when X is at where it is at the start of the simulation, that's a reference point. So leave it alone, right? So we almost always have a ratio on the X-axis. Now we might make it time and then have ordered pairs that are data. So it's not always the case, but that's typically the case. Okay. We also try and think about, when we build these things, what the maximum value is going to be and what the minimum value is going to be. Now, the minimum value is typically going to be this axis, but, you know, 0 might be here. So this might be a negative number down here. It just depends on what you're doing. And then you're on the maximum here. Is this 10? Is it 100? Is it 2? When, well, so you got to define a max and a min. And then you have to decide, is there a negative relationship between the effect and the ratio, or a positive relationship? So when demand is greater than supply, okay, so it's greater than 1, this ratio. And this is the effect on price, or on the markup above unit costs. When the ratio goes up, do we want the effect to go up or down? Do we want price to be higher or lower when there's more demand than supply? Yeah, Naisha's right. She's pointing. So we want the effect to go up. So the shape would be going in this direction, right? And again, if it was opposite, it would, you know, it would be going from northwest to southeast. So you got to know the direction. Now, when you're talking about let's say the maximum values here, you want to say, okay, if demand is twice as big as supply, are we going to raise price by 100%, by 10%, by 2%? Or that might be doubling price, making price 100 times more than it is now, 10 times more. Well, you have to think about, in the real world, what would that be? Make it anything you want, but if you make it a ridiculous number, it's not going to be very meaningful, right? It's going to cause your model to do crazy things. So you have to have some domain knowledge and say, all right, when this grows by, if this doubles, or if it's 50% higher or whatever, what kind of effect do we want, right? We also want to ask the question, you know, what kind of shape do we want here? Do we want it to be more gradual, or do we want it to be more aggressive? Just depends on the situation. You can try different table functions representing different things. You might not know what this shape should be. So you can try different shapes. In the advanced course, the next course, we go into a bunch of math that shows you, for certain table functions, how certain areas here are off limits. They mathematically can't be true. So that your shapes, if the thing has to go through 1, 1 and it can't be over here, there's only so many ways to draw the thing, right? So it's not completely ad hoc, right? So there's logical ways to say, look, the shape is not just spitballing at, you know, there's ways to narrow down what this thing should look like through math and logic. I'll show you in a minute. There's also a way to nail it down using data. Okay, so let's then go to the, Warner Wolf would say, let's go to the videotape. I think it was Warner. So it's a sometimes a table function is called a lookup function, sometimes called a graphical function, depends on whose software package you're using. And you can represent linear, you can make it a straight line. You can turn off a table function by just making it a horizontal line at 1. The effect is always 1, no matter what the x-axis is doing. Turns it off to see what happens if we cancel out that effect. If that effect goes away, what happens now? That's a good thing to be able to do, right? So it's usually nonlinear relationship that is hypothesized to exist between 2 and only 2 variables. What you don't want to do, typically, these are rules of thumb. These are not theorems that hold in all cases, and I can show you a model where this is violent. I've already showed you the model. It's the Urban 2 model. Remember that model, the Urban 2 model, but with a table function. Here's your ratio. You almost never, and here's your effect. You almost never want it to be non-monotonic. Like that. That would be, well, you don't like that. That's non-monotonically increasing. Monotonically would be like this. It could flatten, but not go down and then go. But you don't want a reversal of direction. Same thing here. You don't want it like that. So if you see a table function like that or like that, that's typically alarm bells go off. It's kind of like first order control. Usually you want it, but sometimes you don't. Romeo and Juliet, you don't want it because negative values of the stock mean dislike, right? But usually you want first order control. Well, here, usually you don't want this shape or this shape. Usually if you see a shape like this and this, it means you should have 2 separate table functions. There's probably 2 things going on here. You're trying to smear them together in one place. Rule of thumb, not a theorem. Table functions are not empirically derived correlations of behavior over time, but I'll show you a way to use data anyway to estimate them. Okay. So we kind of talked about all of this already. Talked about that, avoid sharp corner points. You're going to see in Stella, there's an easy way to do that. It's kind of neat. Okay, and the steepening and flattening makes a difference. We talked about is it aggressive or is it gradual? Okay. Kind of a repeat here, this stuff. Okay, so one thing that some people like to do is to say, I don't like these piecewise table functions. Because like with all of system dynamics, we're having steps here and we're joining them together. Now you can have a lot of steps, a lot of points, and it's smoother, but it's still piecewise when you make these table functions. And we try not to have sharp edges, try to make it smooth, but it's still piecewise. So sometimes system dynamicists prefer to have an analytical function that's perfectly smooth. Okay, so I've always been sort of on the lookout for the next greatest functional form where I can say, hey, I can use that for a table function if I elect to use a continuous table function. We'll look in a minute at a traditional table function in Stella and how you can smooth it out and stuff. But so here's the, excuse me, in this case, the function is down here. Y equals a minus d over 1 plus x over c raised to the b raised to the e plus d. I don't remember where I found this. I found it a long time ago. But what's neat about it is A, B, C, D, E all has meaning. So A is the maximum value. I mean, meaning for defining a table function. A is the maximum value. D is the minimum value. It doesn't have to be 0. I've drawn it here as 0. B determines whether or not it goes from southwest to northeast or vice versa. Oddly, if it's less than 0, it's a positive slope. It's usually with a line, it's different. C is where the inflection point is. And then E is the symmetry parameter. Like, does this side look like this side of the thing, or is it asymmetric? It's like this, and then a little bit abrupt over here, or is it very symmetric? And depending what you make A, B, C, D, and E, this thing will look very different. All right. So how would you use data to create a table function? Well, what you don't want to do, although I've seen people do it, it just depends on who you are and what you're trying to pull off. I mean, a lot of this stuff is just rules of thumb. You know, if what you are not supposed to do is you have some variable here, and you have some variable here, and you have that, and then you run a regression through it, it fits like that. And you say, that's my table function, because it's essentially a directional correlation coefficient. And that's your table function. That's not how you're supposed to do it. Now, this could be done. Roger Nail, a very famous SD guy, used to do this all the time, and it was really good, well done. But he had exact data on these concepts. So I don't want to go there right now. That's not usual in system dynamics, but it can be done, and some very good modelers have done it. But I'll show you a different way to derive a table function from data. So so let's use that same concept that I showed you before, where I just said stock and max stock and stock ratio and all that. So now let's make it a little bit more concrete. Let's say we have a building rate and structures in a city. There's an average number of acres each structure occupies. And so the land occupied in terms of acres is, well, the number of structures times the average acre per structure. So structures times acres per structure is acres occupied. Available land is in acres. So the land ratio is now acres occupied over total available acres. When that acreage, or that ratio rather, is 1, it means everything has been built on. So there's an effect of the land ratio on the growth coefficient. So the positive loop is, I want to build my structure near everybody else's structure. I don't want everybody else to be over here, and I'm going to build mine way over here, because everybody's going to go over here to shopping, and my store is going to be way over here with nothing around it. No good. So you want to build, so structures attract structures, right? But as the city grows, or the Diamond District grows, or the Garment District, or whatever, Silicon Valley grows, then you start to run out of either available land, or it starts to get so far away from the core, it's no good. Okay. Now, so you've seen this model already earlier today. Now, pretend this is not a model. Pretend this is the real world. We're going to do a synthetic data experiment. And I'm going to add some noise to the model to make so it's not so smooth and perfect. Okay, and then I'm going to export, well, I'll run the model, and then I'll export the data to Excel. So the Excel spreadsheet would be what you'd find at City Hall for this city here. A spreadsheet full of data on structures and the building rate, land fraction occupied. There'd probably be building permits and stuff like that. This is just to illustrate the table function. This is not the greatest urban model. Okay. So we're going to pretend it's the real world. I've added some noise. We're going to run the model, pretending it's a real city generating real data. And we're going to export the data to a spreadsheet as though it's a spreadsheet residing on a server at for your municipal governance. And you can download the data if you want. So here's the data. Now, let's say I'm going to download that data set, that Excel file, and I'm going to build a system dynamics model here from my knowledge of cities, right? I can look at that and say, the blue line there, and say, all right, there must be a positive loop, a negative loop, a limiting factor, and whatever from my system dynamics knowledge. I just don't know exactly how that table function should look. Okay. So I say, aha, I can take this here, A, B, C, D, and E, in this functional form, and put it inside of effect of stock ratio on growth. So max, slope, inflection, that's A, B, C, D, E, symmetry, and all that. I guess I could have said A, B, C, D, E if I wanted it. Okay. Then I can tell the computer to suck in the data from the spreadsheet. Now it's from the real world, although it's really synthetically generated. But if it were from the real world, right? Suck it in and manipulate the values of these parameters until it fits the data best. And I did that. So over here, it found that these parameters had to be manipulated to these values. So the normal growth coefficient started at 0.2 and it ended up being 0.623 and so forth. It took 483 simulations to find that out. And that's the table function it found. Kind of looks like the one I drew before, not exactly, but sort of, when I did the generic model. And here's how it fit the data to find that. There's the structures. There's the building rate, and you can see it kind of found the middle of the data set, right? And there's the land fraction occupied. Okay. Now, we don't go into how you do that in this class. Import and export data, fit it to calibrate it and stuff. There's a bunch of stuff that has to happen there that's beyond this class. But the other classes get into that stuff. Okay. All right. Now I'm looking at my clock, but I did want to show you, let's see what else I had teed up here for you guys. Do you want to see the leader subordinate model that I know Suzanne wants to see it? So I'm seeing what looks like an enthusiastic yes, although she's muted. We can do that if you want. So we'll take a look at that. This is what I did with the ROTC students. And again, there's a lot of table functions happening here. Oh, by the way, before we do that, let me say this. Over here with this table function, you see it's a little jagged here. There's kind of, it's not perfectly smooth. I can make it smoother by go down here, data points. I just keep adding data points. See how it's smoothing it out? It's kind of like if you make DT smaller, right? So we can smooth this stuff out. The other thing that's cool is you can pick canned functions if you want, and you can make them more or less aggressive at your will. But so you don't have to, you can type in all these ordered pairs here. And if you're replicating somebody else's model or putting in actual data, you got to type all this in or copy and paste from Excel in here. So sometimes you got to do the tedious or a little more tedious. But if you don't have to worry about that, if it's just a canned function, then you can just use these various canned solutions here, and you're good to go, right? It's like that, and just make them whatever you want to be. So you can do them quick, or you can use data. It just depends on what you're trying to do. All right, how about this ROTC thing that Suzanne has wanted to see? Let's see, I gotta remember which is which. No quiz. Okay. So I had some students come to me a couple of years ago. I think it was a couple of years ago. One of them they're all ROTC cadets for the Army. One of them had taken one system dynamics course, but she was majoring in psychology. And she said, you know, as I was taking system dynamics, I realized that, wow, that's a tool I could use for a lot of things in psychology. And I'm also in ROTC, so I'd like to do an IQP with some of my fellow cadets on leader-subordinate interactions. Would I supervise their project? And I said, well, yeah, kind of sounds, you know, interesting. So, okay. Well, what happened was only one team member had some system dynamics. That one person had only 7 weeks of system dynamics undergraduate. So they tried to build a model, and I'd make some suggestions, and it was just terrible. So I just said, all right, you're my clients. You tell me all the domain stuff, and I'll build the model for you. So that's how we did it, and it worked way better that way. So what they said is, all right, the Army has a physical fitness test, and we have many versions of it. I just pulled up a version. I think this might be a recent version, but I'm not 100% sure. But that maxes out at 600 points. It's like a running test, I think. There might be other physical things, but the max you can get is 600.
It is. I'm taking mine tomorrow.
Oh, is it standardized across all the different services?
It's different for Army now. They used to have the same test, but they just made it different. So it's
okay
now.
Okay. Okay, but the max score is whatever, but it was 600 in this case. Okay, and so the idea was that the leader, whether the drill instructor or what, I'm not sure what you call the person who tells you what to do, but their job is to get you to do stuff. And in this case, get a higher score so that when you graduate after 48 months, you've done, at least with the physical fitness part, as best as you can do. So, okay. And so how do you do that? And like the generic problem is, how do you get people to do stuff they don't want to do? That's what leaders do, right? So, so we said there's a physical aspect to all of this. So each person is going to have an amount of energy, okay? And it's going to be rejuvenated through rest, and it's going to be taken away through training, running, let's say. Okay, so you can sleep and you can run, and you're going to deplete and restore your energy. Okay, you get off the bus with a particular constitution. You're a very energetic person. You're kind of slow moving, or you're something in the middle. You're a gym rat. You love going to the gym. You love running. You love working out, or not. So these are parameters for the person when they get off the bus on day one. So they initially sleep so much. Some people need more rest, some others less rest. They work out so much per month, and they have other stuff they got to do besides sleeping and working out. So it's like you do all your other stuff, and then what time remains, you divide between working out and sleeping. Now, you can also drain your energy through not just working out, but through your performance and your perception of how you're doing. So if you get depressed, you can, because you're not doing well, that can zap your energy as well in this model. So there's a psychological state. So motivation is the big deal here, and to get people to do something, in this case, work out more and score better. And people can be intrinsically and extrinsically motivated. So if you're intrinsically motivated over here, the better you do, the more you say, this is great. I can do this. I'm going to work harder. I see myself improving. Or the other way, this is futile. I suck at this. I'm not. And then you can be extrinsically motivated, which is when the leader is either praising you or criticizing you to get you to do better. Okay. but different person. So there's different sensitivities to somebody praising you or criticizing you. Some people, it's water off a duck's back. The Gomer, another old one, Gomer Pyle, where the sergeant is just yelling at him right here, and he's just smiling. You know, he's like oblivious to the water off a duck's back, or they're very sensitive, always said something that, you know, or whatever. So different personalities. So we have table functions here. So in this case, if this personality is in play here, move this over here. You can see that the person responds positively to praise and negatively to criticism. So if you praise the person, they'll try harder. If you criticize them, they're like, you're going to yell at me, I'm going to run slower, you know, that kind of personality. This next personality, they respond to praise and they're indifferent to criticism. You yell all you want, they don't do anything different. Or here they respond negatively to praise and positively to criticism. So if you challenge them or they say you're a slacker or something, I'll show you. But if you praise them, they roll their eyes. Like when your grandmother tells you that you're the best looking student in the school, you're like, yes, grandma, you know, you're rolling your eyes like, yeah, right. Oh, whatever. And then the last one is that you're indifferent to praise, but react positively to criticism. You try harder with criticism. Okay. And you can set how much more you do. There's a sensitivity parameter here. Okay. And then in the performance area, you get a score, your current score, and that's based on, well, what's your energy level, how much are you training, and how motivated you are. So you can be highly motivated to a lot of training, but you're exhausted, so you don't do well, right? You can have a lot of training, a lot of energy, but you just don't care, so on and so forth. And that changes your score. But there's the score on the test, but then we said there's going to be a score on the simulation, because we said it really does you no good to achieve, let's say, a maximum score, or at least the best you can do at the end of your 48 months of training. But then when you graduate, you're totally unmotivated and exhausted. You can barely drag yourself through the ceremony and you don't care anymore because they just beaten it all out of you. But you've got a 600 score. So it's other aspects of your journey to your score. Additionally, are you going up and down and up and down? You're really good, you're really bad, you're really good, or do you smoothly go up to where you max out? So we're measuring the distance you travel with your energy, your depleted, your high, your low, you know, your motivation and so forth, and your score. And we're giving, I think, equal weight to everything in a multi-attribute scoring metric. Then finally, we got the leaders, the leadership sector. So at time 0, we start the model in equilibrium. And so basically, you get off the bus and you take your first test. And whatever your score is, that goes on the clipboard. And the leader says, okay, Johnny is a 400, Sally's a 500, whatever. And then the leader's goal for you at the beginning is what you can do. And then in time, month 1, the leader says, you can do better. Now you can, I think I said 30% better, excuse me here, 30% better, but we can make it any amount better. Okay, and you can turn this on or off. Okay, and as soon as the leader says you can do better, it knocks it out of equilibrium, because the leader's goal for the subordinate is they're not matching anymore. It's your score is below what the leader thinks you can do. There's a gap, right? And then that gap leads to praising or criticizing. So the leadership style is, are you a praiser or a criticizer? So you got to decide in the model one way or the other. That's your sort of way of doing things. Okay. And then you monitor how productive is your praise or criticism? Is it getting you anywhere? Every time I yell at this guy, he runs faster. I'm getting somewhere. Every time I yell at this guy, nothing happens or he runs slower. No good. So you can also set up the leader to be adaptive or stubborn in their leadership style. I'm a criticizer, and that is how I've done it. I've done it this way for 30 years. It's my way or the highway. We're going to do it this way. Or if you see I ain't getting anywhere yelling at the guy, I'll start yelling less or start praising, and vice versa. Praising this guy doesn't work. He sees it as weakness. So I'm going to start kicking him in the pants. So you can set up the person, the subordinate and the leader any way you want at time 0. Okay. So in this case, I don't remember what I did here. We did this a while ago, but so here's just some basic stuff. I think this is equilibrium. So start in equilibrium. I think this is out of equilibrium right here. Leadership style. There's a little bit of a change there. I don't know what's going on there, but this is, you got like 75 different versions of this thing running around. But so then we can go over here to the leadership thing, and we can say, let's turn on the shock. So now we're going to shock it out of equilibrium. And let's see, is it this guy adaptive or not adaptive? Switch for leader. They're not adaptive. What happens now? So we're going to shock them out, and they're not adaptive leader. Okay, so energy goes way down. What do we got here? Performance score is, oh, what happened there? Oh, did that thing close? Oh, it went away. Oh. I'm not going to reopen it. I don't know why that disappeared on me. In the interest of time, already over time. Then we made a game out of it. Okay. And in the interest of time. So now to make a game out of it, you have to sever the leadership stuff because it's all endogenous, and you let a leader play the game. And in this case, we don't know what the personality is of the cadet or the subordinate, right? We're starting 0. So we're not a praiser or we're not a criticizer. And we're starting with a goal of 400, which is equilibrium. So if we run the model forward, we're in equilibrium. Nothing happens, which you can just leave it be. Let's say now we have a goal of 500. So, all right. So the goal jumped up here, right? And the person's score is falling. Overall simulation score is falling. Okay. So what are we going to do to address that? So you want to praise them or criticize them? You want to yell at them or pat them on the back?
Criticize.
You want to do it a lot or a little?
A little.
Oh,
Oh,
what do you want to do? You can
now we
drop,
have to, now we're going to have to
drop
praise
the
them a
goal.
lot because it takes 5 positive interactions to overcome 1 negative interaction.
all right, so let's praise them a bunch. Oh, your motivation's going up now. Energy levels down. Overall score is better. Now they're testing better. What do you want to do?
Praise them a lot again.
Same amount or more?
The same amount. I don't have any more in me.
Oh, we're plateauing here. Okay, energy level is going up a little bit. Motivation is rolling over.
Criticize
A lot or a little?
a lot. They can do a lot better. I don't think they're really trying.
Okay. Motivation is way down because you're yelling at me. What do you want to do?
They tanked now.
What do you want to do? Graduation is coming.
Praise them a lot.
Okay.
Oh.
Motivation is reversing. Okay.
It takes them a long time to recover
One-
from those criticisms.
Okay, one
Praise
more.
praise a little now, just a little bit.
Okay. So the overall score was 115. You started at 100. 100 is like you do nothing. So you did a little better, but you didn't reach the goal of a 500 on the score. Their energy level has dropped. This isn't the greatest graphic. We need more information here. Motivation is all over the place. You're gung-ho, you don't care, you're gung-ho, and so you get the idea. So this is one of these models where before I run it, I have no idea what the hell's going to happen, honestly. There's so many non-linearities and things. So what we did with it was we the junior year project, the IQP ended. It was 3 students. 2 of them said, thanks, that was fun. See you when I see you. The one psychology major in her senior year said, I want to pick up the IQP model and I want to make a game out of it and have human subjects, cadets, play the game. So we did the game. Now that was just my goofing around, and then I gave her some suggestions and she did a whole thing, and had to go through the IRB and get permission to run the experiment on human subjects. She had to do a quiz before the psych professors made her, each player do a quiz. They couldn't play the game till they passed a quiz that said, yes, I went and I explored the model and the background information and all that stuff. And then they had like 54 cadets. I guess is it a battalion? It was like UMass Lowell, WPI, and maybe another school. They had their joint meetings. They had like 54 cadets play the game, and they were given 5 plays of the game, and we're going to take their best score. And Michaela thought, oh, they're going to be like whatever. And she said it was amazing. People didn't want to stop playing after they got to their 5 because they wanted a better score. They're like really engaged in this and whatever. And what she tested was half of the group, she let them know the personality traits and all that stuff for the cadet, for the subordinate in the game. And the other half had no idea what they were dealing with. And there was a definite difference in average score between the 2 groups, but it was not statistically significantly different. Although she was running out of time. We could have done more. So I think there might be some, but it was interesting because either way, there were significant implications. If there had been statistically significant differences between knowing who you're dealing with and not, then that suggests to the Army, you better give each drill instructor a binder. Well, first give a test, physical and psychological, to everybody, and give them a profile and say, this person you yell at, this person you praise, this person, if you praise them, they're going to roll it, and it matters for getting them to do stuff. Whereas if what we found, and again, I think we could do more, is it doesn't matter. You don't have to know, just adapt as you see them, whatever you see them doing, go with it or go the opposite way, and you're good to go. So I think there's quite a lot there that could be done. I mean, Ashley, you're in the service, so you might have more, you might think it's all nonsense, and because I'm not in the service, you are, so you might have thoughts about this that are different from mine. But it seemed to me a very interesting model and project, and like with the undergraduate stuff, it's they got to get stuff done in 7 weeks and then it's over, so we got it as far as we could go, but there's probably a lot more that we could do if folks were interested. But
Maybe I can
Just
try on
to-
my cadets.
Sorry?
Could I get experimented on my cadets, extend the experiment?
Yeah, possibly, yeah. So the version that she did is much more complicated, and it takes longer to load because there's all sorts of military pictures in it and stuff. She did a very, very nice job. And there's a way to get Stella to record what everybody's doing behind the scenes, so you can analyze and it was neat when you looked at what people were doing. You see all their decisions when they moving the sliders and changing the goals and all that stuff. So you could do a lot more with like, well, what are people doing here, and trying to get this avatar to do what they want the thing to do,
I just had a quick question about that. So like the cockpit, is it giving you randomly a different cadet with a different personality profile each time you play? And they
You could
keep
make-
that
you could make-
personality and you
Yeah, you
keep
could-
that personality constant during the game,
He kept it constant during the game, but you could say.
and then it's a random one, it's a different one every time you play. So you
No,
just don't know.
with her thing, she just either the person's knew or they didn't know, and it was the same personality and physical and all that. But you could absolutely say you could have a whole bunch of different, because think of the different combinations of psychological and physical characteristics of each person. I don't know how many combinatorics, it's probably millions. So you could pick 20 representative sort of personality traits and physical traits and all that, and then have the computer randomly select one, so you don't know who you're dealing with when you go to play the game, right? And we did it on 6 months because we didn't know, so it's like, well, would people stick around for we had to go 6 months and stop. What if they went 3 months and they could make more decisions, or would they be goofing around? So we didn't really know, but it would be more interesting to have more decisions to make, to analyze as well. And so forth. So this is what I'm saying. This is the kind of thing where you could spend oodles and oodles of time really doing a deep dive on it, and you devising once you've got something that is really solid, you could then devise a survey instrument or something to correspond to it, where you could take somebody and say, this is Johnny, just got off the bus here, put his characteristics in here, right? And see how, and then we'll let drill instructor Sally deal with this guy now in the simulator and see what, that would be kind of, but we're nowhere near that. But I mean, that's a kind of thing, I suppose, that could be done here. Now, again, does the service care? I'm guessing you want to make people do stuff. Well, but I'm spitballing here. It's really, I defer to Ashley or folks who do it for a living as to what questions they might want to answer. But this is the kind of thing where there's a lot of physical, psychological, hard, soft, all sorts of stuff interacting. Limiting factors, there's only so many hours in the week or in the month, right? So on and so forth. Right?
Right.
I think the real I mean, I'm thinking about this in terms of like a marriage, for example, and as a learning tool for teaching people that you have a choice about how you respond to the person that you're dealing with. And if you can
Family
become
dynamics.
yeah. If you can
Smart
become
ass
a
kids,
student
smart ass
of
teenagers,
them
whatever, yeah.
and learn how they're wired, you potentially can exert influence. You can't control people, but you could exert influence over them based on how you choose to respond. And even if, I mean, the game could help people grasp those concepts in a way that I think many people do not. It's always everybody else's fault, not their own fault. They don't recognize the concept of endogenous behavior, for example, and how that affects the system. And so I think this is a very provocative model in a lot of different settings. Students, training, I mean, it's the whole idea is the way I choose to respond is a mechanism of influencing those around me in whatever the relationship is. And it's really valuable from that perspective, I think.
Yeah. Fun project. Again, I offer it to you as this is some of the stuff we've done recently. And if it stimulates your thinking, cool. You see some table functions in action there. Those table functions are super important in the model to defining somebody's psychological responses to external stimulus or leadership pressures, motivation, or whatever you want to say. So and they're nonlinear, right? So that's the kind of thing where this stuff shines, these table functions and whatever. Okay, I'm looking at my clock. We're a little bit past again. So, but anyway, I seem to think that this would be interesting to take a look at.
So Ashley, next week you have to tell us how you do on your test tomorrow.
All right, I will.
Yeah.
It's gonna be cold.
So we'll leave it there. We're making good progress. So before we go, where we're headed then is the next simulator we're going to look at, there's not enough time now, is managing deer on the Kaibab Plateau. So it's not S-shaped growth, but it's overshoot and collapse. It's kind of a miniature world dynamics thing. And you'll start to see policy space in action. And we'll start to think about, you know, what works in the model, and then can you pull it off in the real world? Because it does no good to say, look at this elegant mathematical solution, and then the real person in the real system who has to deal with the real problem says, I don't know what that means. I don't know what to do. It doesn't help me. But look at the elegance of my model. The brilliance. See, so cool that it's elegant and brilliant, but can a real person in the real system based on your model pull off something that makes the system better? So we're going to be looking at policy space, and it's not just this S shape, but the collapse, or stopping the collapse and getting the S shape. Okay. Then after that, we're going to start building a model from scratch. We're going to read a newspaper article and say, what's the problem? And we're going to go all the way through and build the model. And we'll see if we can even turn it into a little game. Then we'll look at a couple more really big models that are sort of in this genre. And then we're getting towards wrapping things up. We'll start to talk about, how do you know your model is valid? How do you know your results are robust and won't fall apart at the first opportunity? How do you put a model into equilibrium or some other state to start it? It's a bunch of, we'll just touch on these topics because they in and of themselves are big, gargantuan things a lot of times, but we want to make you aware that there are other issues, including how do you document and write up a model for a journal or a report or something, so that others can reproduce what you've done. Because replicability is a hallmark of science. And if you got this brilliant result, but nobody can repeat it, it's called into question, right? Cold fusion, but nobody could replicate the results, right? It's like, I don't think so, right? So some of the stuff is more mundane. How do you document a model? You know, boring, but still very, very important. So this is where we're headed over the last several weeks, and we'll get as far as we can in the time that remains, and as well as interest is there. Then we'll regroup and figure out what the heck we just did for the last several months.
Okay. Awesome.
All right, we'll leave it there. We'll see y'all next week.
Thanks so much, Mike.
Bye-bye. You're welcome.
Bye.
Bye.